Welcome to The Explainer. Today, we're taking a super fascinating journey into something that's literally happening all around us and, well, even inside us, right at this very second. We often look at chemistry as just this set of dry, rigid textbook rules we have to memorize. But let's shift that perspective today. We're going to look at chemistry as the secret, dynamic language of the physical universe. It's basically the source code that dictates how matter transforms, creates, and sustains our whole world.
Okay, so let's dive right into this. I absolutely love this quote from Martin H. Fisher. Facts are not science, as the dictionary is not literature. It hits the nail on the head, right? Just knowing that water is H2O isn't really doing science, just like knowing word definitions doesn't mean you've written the next great novel. So today, we're going to learn how to take the raw words and facts of chemistry and actually string them together into meaningful scientific literature by understanding chemical reactions.
Here's our roadmap for today's explainer. We'll start by looking at the signs of a reaction, then we'll learn the chemical alphabet. From there, we'll balance the scales, explore combination and exothermic reactions, and finally, look at the art of decomposition. Starting off with Section 1, Signs of a Reaction. So before we can write out the language of chemistry, we kind of need to know how to spot these physical conversations happening out in the real world. And that brings up a really great question. How do we actually know a chemical reaction happened at all? Just think about the everyday chaos around your house. Say milk gets left out on the counter on a hot summer day and goes completely sour. Or maybe grapes start fermenting. Or an iron pan is left out in the humidity and starts rusting over. In all of these everyday situations, the original identity of that substance has fundamentally changed. And that, right there, is a chemical reaction. According to our source material, there are 4 real telltale physical signs that a reaction just went down. We're looking for a change in state, a change in color, the evolution of a gas, or a change in temperature. Let's say you take a few solid zinc granules and drop some dilute sulfuric acid onto them in a flask. You're going to immediately see these bubbles of hydrogen gas forming all around that zinc. And if you were to physically touch the flask, it would actually feel hot. So a gas evolved and the temperature changed. Boom! Reaction confirmed. Moving right along to Section 2, the chemical alphabet. Okay, now that we know how to spot these changes, how do we write them down? Well, we start with our ingredients, the stuff that's about to undergo a change. We call these the reactants, and we always put them on the left-hand side. Then we draw a directional arrow pointing over to the right, basically saying this turns into. And on that right-hand side, we write out the brand new substances formed during the reaction. We call those the products. Now, writing out magnesium plus oxygen becomes magnesium oxide in full words every single time, that gets clunky fast. So instead, we use chemical formulas to create this really sleek shorthand script, which we call a skeletal equation. Let's say you take a magnesium ribbon and burn it in the air. It burns with this dazzling white flame and literally turns into a white powder. In our chemical shorthand, we don't write a paragraph. We just write Mg plus O2, arrow, MgO. It's concise, it's elegant, and it tells you exactly what elements are interacting. All right, let's head into Section 3. Balancing the scales. Now, there is a slight catch with those skeletal equations we just talked about. The absolutely crucial thing to remember here is the law of conservation of mass. Mass can neither be created nor destroyed in a chemical reaction. You can't just have ingredients magically appearing out of thin air or vanishing into the void. It just doesn't work that way. The total mass of your reactants has to be exactly equal to the total mass of your products, which means the number of atoms for each specific element has to be exactly the same before and after the reaction happens. To actually pull this off without pulling our hair out, we use a really logical, step-by-step problem-solving process called the hit and trial method. This totally prevents cognitive overload. Step 1. Draw boxes around each chemical formula. And listen, you can never change anything inside those boxes. You can only add numbers in front of them. Step 2. List out the number of atoms for each element. Step 3. Start by balancing the compound that has the absolute most atoms. Then, finally, you just equalize the remaining elements one by one. Let's think about a before and after scenario where iron reacts with water to form iron oxide and hydrogen. If we just write the basic skeleton, the scales are completely out of whack. We'd have 1 iron atom on the left, but 3 on the right. 1 oxygen on the left, but 4 on the right. No way that works. To fix this, we have to multiply our molecules. We'd put a 3 in front of the iron reactant and a 4 in front of the water reactant. That balances our iron and oxygen, and then we just tweak the hydrogen product on the other side to match it up. See? Beautiful, perfectly orderly grammar. Next up, Section 4, Combination and Exothermic Reactions. So as we start categorizing the different types of chemical sentences, let's kick things off with reactions that build things up. A combination reaction is exactly what it sounds like. 2 or more substances combined to form a single product. And you know what's cool? Often when this happens, a huge amount of heat is evolved, making the whole mixture warm up. We call these exothermic chemical reactions. Exo meaning outside and thermic meaning heat. So the chemical bonds forming are literally releasing energy outwards into the environment. To ground this in biology for a second, you might be surprised to learn that you yourself are a walking, talking exothermic reaction. I mean, we all need energy to stay alive, right? And we get that from food. Our bodies break down carbohydrates into glucose. Then that glucose combines with oxygen inside our cells to provide energy. This reaction is called respiration, and it's a constant, life-sustaining exothermic process happening inside you right this very second. Here's another really fascinating real-world application. When you take calcium oxide, which is commonly known as quicklime, and you add water to it, it reacts super vigorously to produce a single product called slaked lime, and it releases a massive amount of heat while doing it. But here's the best part. A solution of this slaked lime is actually used to whitewash walls. Over the next 2 to 3 days, it slowly reacts with the carbon dioxide in the air to form this thin, shiny layer of calcium carbonate. It literally creates the exact same chemical compound as marble, right there on the wall. How cool is that? And finally, Section 5, the art of decomposition. Using the rule of contrast here, let's pivot from reactions that build things up to reactions that break things down. Now, these equations aren't just abstract math problems floating on a chalkboard. They represent real physical actions that require specific laboratory tools. In a decomposition reaction, a single reactant breaks down to give us simpler products. Often, to make this happen, you have to actively apply intense heat to a boiling tube, maybe holding something like crystals of ferrous sulfate or lead nitrate. And when decomposition is driven by heat like that, we call it thermal decomposition. Now, because decomposition reactions require energy to break apart the bonds of a single reactant, they're known as endothermic reactions, meaning energy is absorbed rather than released. And it doesn't always have to be a flame doing the work. Energy can be supplied as heat, sure, but also as electricity or honestly, even just light. For instance, if you put some white silver chloride powder in a little dish and just leave it sitting out in the sunlight, the light energy is absorbed, the powder literally decomposes and turns into gray silver metal and chlorine gas right before your eyes. And that brings us to the end of today's explainer. I really want to leave you with this final provocative thought.
What invisible chemical scripts are being written right in front of you today? I mean, from the slow rusting of a nail in your yard, to the digestion of your morning breakfast, to that shiny marble-like finish drawing on a wall, our world isn't just some random collection of static objects. It's a highly active, continuously balancing mathematical equation. And the more you learn this alphabet of chemistry, the more you can actually read the incredible literature of the universe. Thank you so much for learning with us today.